Is chinedu, ukeje, and my project topic is predicting greenhouse gas emissions characteristics of the United Kingdom using deep learning algorithm. The United Kingdom, as we know, has is the fifth largest economy in the world, which means it attracts a lot of talented individuals into the country to make a living. What this means is that at the end of the day, there's a population spike, which all contributes to greenhouse effects or greenhouse gas emissions in the UK. The United Kingdom must come up with an ambitious plan to get to a net zero CO2 emissions by 2050. And this project is designed to predict and give a forecast of future predictions of CO2 emissions into the future and to see if this is meeting the trend that's actually in line with the proposed net zero emissions by 2050. Um, the research questions to be answered by this project are shown here. What are the percentage of contribution, which is the first one, of each country in the UK? The second one is to determine what part of the economy actually contributes more to CO2 emission. The third one is to determine what region suffers the most from CO2 emissions. And the fourth one is to determine if there is a discernible trend in CO2 emission from year to year. And the fifth one is to see if there is significant seasonal differences in CO2 emissions from year to year in the UK. And finally, the last one is what future temperature changes can be forecasted based on past and, of course, current emissions data. Now, um, the literatures were considered, were looked into, and the reviewed literature showed different models have been used for the purpose of trying to forecast CO2 emissions. One of them is ARIMA, then the SARIMAS, LSTM. But in all of these, the random forest, support vector regression, K nearest neighbor, it was reported that according to the literature's revealed that LSTM actually does perform better than these other algorithms, and we'll put that to test in this project. Finally, there's technology review in terms of the kind of technologies that is needed to actually carry out this type of analysis, and they all discussed here in chapter 2. In chapter 3, it came up with the methodology of solving the problem, and as you can see in the methodology diagram, the first step is to get the data sets, after which there's data pre-processing, feature selection, and we have a new clean database that is ready to be used. Exploratory data analysis is performed on the dataset. The clean dataset is then split into two datasets, which is the training set and the test set. The training set is used to train and perform evaluation on the models, while the final test set is used to give a final evaluation of the model. Finally, the results are presented and evaluated and discussed as data story. The data that was used for this project was actually gotten from the National Statistics, National Office of the National Statistics of the United Kingdom, and was further augmented by data from the Department of Business, Energy and Infrastructure, and of course some data gotten from Statista. Um, the data was, of course, contained some null values and wrote some functions to clean those values at the end of the day to get a clean data that is usable with zero non values, null values rather. Um, Secondly, and to answer the first question, research question, what percentage of contributions for each country in the United Kingdom, as you can see, England actually generates the highest amount of CO2 in the four countries put together, while Northern Ireland happens to be the least in terms of CO2 generation, as you also see right here. But say putting it this way is not enough to just say England is the highest. What is the population of Ireland? Was the population of England, and how does this impact on CO2 emissions? This was further looked into in the project work, and then the populations, the media population the countries by regions were also looked into and put it into context to say that this truly England is the highest producers of CO2 emissions. To answer the second question, what sector of the UK contributes more in terms of CO2 emissions? Surprisingly, household um, really contributes to CO2 emissions and energy supplies as well. Why there's remarkable drop in CO2 emissions starting from 2010 onwards, you can see there is the household stayed fairly the same, and one of the reasons is most of the time during winter and the COVID period, most people stayed back at home because they lost their jobs, and which of course accounts for the drops here, especially the sharp drops here, and the bond, of course, they used CO2, they emitted CO2 while they were at home. The third question was what region of the UK have suffered the most from this region? It is clear that the regions with the highest population, according to CO2 generations, which is basically England, would suffer more. As you can see, London, Yorkshire, and Humber with Northeast are really have actually suffered more in terms of CO2 emissions as their population contributes largely to the population of England in general. Um, Finally, the LSTM model was discussed, and there was some in terms of the structure and the math behind it, the input gates, the output gates, and of course the forward gates was discussed in the write-up. Then come implementation. In implementation, the first thing was data preparation, as discussed before, cleaned and make sure they are good and no null values. And all other aspects was dropped because we needed the year and the emission values for for each year, the territorial emission value for each of the years. And there is this lovely output here where we talked about the contribution of sectors in terms of um, CO2 emissions. As you can see clearly, energy supply, residential area are really playing big parts in CO2 emissions in terms of sectors. Finally, we need to start the analysis. But before then, the first thing to do is to test for stationarity of the data set to determine if the data set is stationary or not. Now, to do this, there is a test called the Dickey-Fuller test, but this is not, of course, not the only test that can be used to do this. We have moving average trend filters, polynomial fitting, Boscos transformations, and long transformations that could do same thing. But Dickey-Fuller test actually performs very well, and the hypothesis is simple. The test is formulated as follows. The null hypothesis, the time series has a unit root, which means that it's non-stationary, and the alternative hypothesis is that it doesn't have root, unit roots, which means it's stationary. And from our case, after running the Fuller test, it can easily be seen that we have minus a. The test statistics is way less than the critical values, and we can, of course, authoritatively say with 99% confidence that the dataset is stationary. After which we went on to decompose the dataset to see the trend, seasonality, and residue of the dataset as shown here. It's clear that there's a downward trend in in the dataset, and seasonality is something I was to discuss. Now, talking about the trend and seasonality, to answer the fifth question in the research question, is there any significant seasonal difference in CO2 emissions in the UK from year to year? It is obvious from the decomposition of the dataset there is no seasonality in the dataset. Yes, you can clearly see like literally no seasonality in the dataset, and hence we can see there is no seasonal difference between CO2 emissions in the UK from year to year. And the other question to be answered, which is the fifth question to be answered, um, is there any discernible trend in CO2 emissions in the UK from year to year? And to do that, we run the autocorrelation function both partial and full autocorrelation functions. And an alternative way to do that is to run a log plot and see if there is some correlations between the data points from year to year. As you can see, there's strong correlations between the data points from year to year. And to answer that question, it is clear that there is obviously some correlation between the data points from year to year. So what this means is that there is a downward trend in CO2 emissions of the UK from year to year. It is obvious that there is a sharp dip in, of course, CO2 emissions towards the COVID-19 period, basically, but it can still be seen that there is correlation from year to year. Finally, model selection. We considered four different models for use for this particular project. The auto regression model was considered. The ARIMA model was also considered. Finally, exponential model, exponential smoothing was considered. And finally, the LSTM model was considered. After the whole thing, results was evaluated, the ARIMA model, the regression model, the exponential smoothing model, and finally the LSTM model. It's clearly from the graph, we can clearly see that the LSTM model models the flow of data almost exactly as the real one, which of course makes sense compared to the other plots. And in order to evaluate the model, the root mean square error of the models were used as an evaluation matrix, and this was considered the root mean square error is an error, which means that the lower the value, the better the model. As a matter of fact, and zero indicates that the model is 100% perfect, which of course nothing is 100% perfect in reality. And anything closer to zero is what we want. And the output is here. LSTM has 13.693, while the largest, which is the exponential model, has 25.624. And this is plotted here for clarity. So definitely we picked the LSTM model to perform the future prediction, which of course answers the last research question, which is the forecast. And we can see we did a 12-year forecast from 2022 to 2033, and the values out there. Finally, we compared the values of the forecasted by the model with the values of the departments for business, energy, and infrastructure values right here. Compared both of them side by side and showed them in a line plot. As you can see, the departments of business, energy, and infrastructure is, has this straight line prediction, while the model has this dip here in 2023 and another dip here in 2026, which of course for me closely um, shows what the model looks like, previous data points looks like, as compared to this smooth straight line with what that was predicted by DBEIS. And it is obvious that the model performed very well, showing only little differences starting from, of course, the year 2025 to the year 2033. In conclusion, I intend to publish this work, and I've considered some few journals like the Renewable Energy and Sustainable Energy Reviews, Science of the Total Environment, and of course the Environmental Technology um, um, paper, journal. Then I have the plots, my Jupyter notebook where I did perform the analysis, as you can see here, and the displays, as you can see right here. Exploratory data analysis as performed can be seen right here, and then finally this part of the work shows the model after cleaning and condensing the data. The models were then the Kifula test, as you can see, the decomposition, auto regression, the log plots, and the setting up of the four models and the measure of the RMSE We had discussed the SARIMAs for the ARIMA and the RMSC, as you can see, 19.6 for ARIMA. Then that for auto regression, as you can see, 18.040, and exponential smoothing in right here with RMSC of 25.69 for year. Then finally the LSTM model, as you can see right here, with an RMSC of 13.6931, and of course see the plots as lovely traces the data points very well. So after this, finally put it online to make a prediction which you can clearly see right here, and the LSTM model and the years that was predicted. So finally, that is it for me. Um, Thank you for listening and watching. Hope it made some sense to you as well. Thank you.